Welcome everyone to the second video lesson for Chapter 7 of the Foundations of Scalable Systems. In this lesson I'm going to show how the generic concepts I introduced in the previous lesson are translated into an actual technology known as RabbitMQ. RabbitMQ is one of the most widely utilized message brokers in distributed systems. You'll encounter deployments in all application domains, from finance to telecommunications to building environment control systems. It was first released around 2009 and has been developed into a full-featured open-source distributed message broker platform with support for building clients in most mainstream languages. In RabbitMQ, producers and consumers use a client API to send and receive messages from the broker. The broker provides the store and forward functionality for messages which are processed in a FIFO manner using queues. The broker implements a messaging model based on the concept of an exchange, which provides a flexible mechanism for creating messaging topologies. An exchange is basically an abstraction that receives messages from producers and delivers them to queues in the broker. Producers only ever write to an exchange. Messages contain a message payload and various attributes known as message metadata. One element of this message data is the routing key, which is a value used by the exchange to deliver messages to the intended queues. The example here on the slide shows an exchange that routes messages to queues based on the routing key value. This particular message, the routing key value, is France. Consumers bind queues to the exchange with the value that they wish to receive, namely France, Spain, or Portugal. When a message arrives from the producer, the exchange uses the attached routing key to deliver the message to one of the three attached queues. Exchanges can be configured to deliver a message to one or more queues. The message delivery algorithm depends on the exchange type and rules called bindings, which establish a relationship between an exchange and a queue using the routing key. The three most commonly used exchange types are shown here on the slide. Direct exchanges are typically used to deliver each message to one destination queue based on matching of the routing key. Topic exchanges are more flexible, and they provide a mechanism based on pattern matching that can be used to implement a sophisticated publish-subscribe messaging topology. Fan-out exchanges provide a simple one-to-many broadcast mechanism in which every message is sent to all attached queues. This code shows an excerpt of how a direct exchange is configured and utilized in Java. RabbitMQ clients, namely producers and consumers, use the channel abstraction to establish communications with the broker. There's more on channels coming up very soon. The producer creates the exchange in the broker and publishes a message to the exchange with the routing key set to France. A consumer creates an anonymous queue in the broker, binds the queue to the exchange created by the publisher, and then specifies that messages published with the routing key France should be delivered to this queue. Each RabbitMQ client connects to a broker using a RabbitMQ connection. This is basically an abstraction on top of TCP/IP and can be secured using credentials or the TLS protocol. Creating connections is a heavyweight operation requiring multiple round trips between the clients and server, and hence a single long-lived connection per client is the common usage pattern as shown here on the slide. To send or receive messages, clients use a connection to establish a RabbitMQ channel. Channels are logical connections between a client and the broker and only exist in the context of a RabbitMQ connection, which is shown here on the slide. These channels are then multiplexed over this connection to send messages to the broker. So multiple channels can be created in the same client to establish multiple logical broker connections. All communications over these channels are multiplexed over the same RabbitMQ or TCP connection, as again shown on the slide. Creating a channel requires a network round trip to the broker. Hence, for performance reasons, channels should ideally be long-lived, with channel churn, namely constantly creating and destroying channels, definitely avoided. To increase the throughput of RabbitMQ clients, a common strategy is to implement multi-threaded producers and consumers, as shown again on the slide here. Channels, however, are not thread safe, meaning every thread requires exclusive access to a channel. This is not a concern if your client has long-lived stateful threads and can create a channel per thread, as shown on the slide here. You start a thread, create a channel, and publish or consume away. This is the channel per thread model. If you're using an application server such as Tomcat or Spring, however, the solution is not quite so simple. The lifecycle and invocation of threads is controlled by the server platform, not your code. To address this, we need a solution that creates a global channel pool upon server initialization. The pre-created collection of channels can then be used on demand by server threads without the overhead of channel creation and deletion per request. Basically, each time a request arrives for processing, the server takes a number of steps as illustrated in the code here. First, it retrieves a channel from the channel pool. It sends a message to the broker, and then it returns the channel to the pool for subsequent use by another thread. While there's no native RabbitMQ capability to do this, in Java you can utilize the Apache Commons pool library to implement a channel pool. The complete code for this implementation is included in the book's accompanying code repository. The following snippet shows how a server thread uses the borrow object and return object methods of the Apache generic object pool class. You can tune the minimum and maximum number of size of the object pool using setter methods to provide the throughput that your application desires. On the consumer side, clients create channels that can be used to receive messages. Consumers can explicitly retrieve messages on demand from a queue using the basic GET API, as shown in the example here on the slide. This approach uses the pull model, i.e. polling. Polling is inefficient as it involves busy waiting, obliging the consumer to continually ask for messages even if none are available. In high-performance systems, this is probably not the approach you're going to want to use. The alternative and preferable method is the push model, as I explained in the previous video lesson. The consumer specifies a callback function that is invoked for each message the RabbitMQ broker sends or pushes to the consumer. Here you can see the callback function. Consumers issue a call to the basic consume API, and when a message is available for the consumer from the queue, the RabbitMQ client library on the consumer invokes the callback in another thread associated with this channel. The code on the slide is an example that shows how to receive messages using an object of type default consumer that is passed to the basic consume method to establish a connection. Reception of messages on a single channel is single-threaded because channels are not thread-safe. This makes it necessary to create multiple threads and allocate a channel per thread or channel pool in order to obtain high messaging consumption rates. The code on the slide here shows an extract of how this can be done. Each thread creates and configures its own channel and specifies the callback function, thread callback in this case, that should be called by the RabbitMQ client when a new message is delivered. Another important aspect of RabbitMQ to appreciate in order to obtain high performance and scalability is the thread model used by the message broker. In the broker, each queue is managed by a single thread. This means you can increase throughput on multi-core nodes if you have at least as many queues as cores on the underlying hardware. Conversely, if you have many more highly utilized queues than cores on your broker node, you're likely to see some performance degradation. Like most message brokers, RabbitMQ performs best when consumption rates keep up with production rates. When queues grow long, in order of tens of thousands of messages, the thread managing a queue will experience more overheads. By default, the broker will utilize 40% of the available memory of a node it's running on. When this limit is reached, the broker will start to throttle producers, slowing down the rate at which the broker accepts messages until the memory consumption drops below this 40% threshold. The memory threshold is configurable, and again, this is a setting that can be tuned to your workload to optimize messaging throughput. All messaging systems present a dilemma around a performance versus reliability trade-off. In this particular case, the core issue is the reliability of message delivery, commonly known as data safety. You want your messages to transit between the producer and consumer with the minimum of latency, and of course you don't want to lose any messages along the way. Ever. If only it were all that simple. These are distributed systems, remember. When a message transits from a producer to consumer, there are multiple failure points you have to understand and cater for in your design. These are shown on the slide. If your application can tolerate message loss, then you can choose options that maximize performance. It probably doesn't matter if occasionally you lose a message from an instant messaging application. In this case, your system can ignore message safety and run at full throttle. This isn't the case, say, for a purchasing system. If purchase orders are lost, the business loses money and customers. You need to put safeguards in place to ensure data safety. RabbitMQ, like basically all message brokers, has features that you can utilize to guarantee end-to-end message delivery. These are shown in 3 categories on the slide here. Let's go through them in turn. First is Publisher Confirms. A publisher can specify that it wishes to receive acknowledgements from the broker that a message has been successfully received. This is not the default publisher behavior and must be set as a channel attribute by calling the Confirm Select method. Publishers can wait for acknowledgements synchronously or asynchronously by registering a callback function. You can also specify that the broker should use persistent messages and queues. If the message broker fails, all messages stored in memory for the queue are lost. So to survive a broker crash, queues need to be configured as persistent or durable. This means messages are written to disk as soon as they arrive from the publisher. When a broker is restarted after a crash, it recovers all the persistent queues and messages. In RabbitMQ, both queues and individual messages need to be configured to be persistent to provide a high level of data safety. Finally, we have consumer manual acknowledgement. A broker needs to know when it can consider a message successfully delivered to a consumer, so it can remove it from the message queue. In RabbitMQ, this occurs either immediately after a message is written to the TCP socket or when the broker receives an explicit client acknowledgement. These 2 modes are known as automatic and manual acknowledgements, as I've talked about already in this lesson. Automatic acknowledgements risk data safety, as the connection or the consumer may fail before the consumer processes the message. For data safety, it's therefore important to utilize manual acknowledgements to make sure a message has been both received and processed before it's evicted from a queue. In a nutshell, you need publisher acknowledgements, persistent queues and messages, and manual consumer acknowledgements for complete data safety. Your system will almost certainly take a performance hit, but you won't lose messages. As I described in the previous lesson, a single broker is a single point of failure, and hence the system will be unavailable if the broker crashes or experiences a network failure. The solution is broker and queue replication. RabbitMQ provides 2 ways to support high availability, known as mirrored queues and quorum queues. While the details in implementation differ, the basics are the same. Namely, you have 2 or more RabbitMQ brokers that need to be deployed and configured as a cluster. Each queue has a leader and 1 or more followers. Publishers send messages to the leader, and the leader takes responsibility for replicating each message to the followers. Consumers also connect to a leader, and when messages are successfully acknowledged at the leader, they're removed from the followers. There are numerous differences in the exact features supported by quorum and mirrored queues. Quorum queues must be persistent and are therefore designed to be utilized in use cases when data safety and availability take priority over performance. They have other advantages over the mirrored queue implementation in terms of failure handling. For these reasons, the mirrored queue implementation will be deprecated in future versions. So use quorum queues. So there you have it for an overview of the major features of RabbitMQ. It's a widely used distributed messaging platform and one that you could easily use in your own systems to provide asynchronous messaging. In the next lesson, I'm going to talk about a few generic messaging patterns that you should consider implementing in any messaging system to provide you with a high-performance, scalable, and robust system. Thanks for watching.